Hello, students. Let's begin with an exciting thought. Have you ever wondered why diamond sparkles, why salt crystals are hard, or why metals conduct electricity so well? The answer lies in the way atoms and molecules arrange themselves in crystalline solids. Crystalline solids are broadly classified into four types: molecular solids, ionic solids, covalent or network solids, and metallic solids. Each class is distinct because of the type of particles that make them up and the forces holding them together. These structural differences decide whether a solid will be soft, hard, brittle, shiny, or a conductor. Let's explore these one by one.
Molecular solids are fascinating because they are made up of molecules held together by weak van der Waals forces. Since these forces are not very strong, molecular solids are usually soft, they have low melting and boiling points, and they can even be volatile. That's why dry ice, which is solid carbon dioxide, easily sublimates directly into gas. They are poor conductors of electricity because no free electrons or ions are present. Examples include dry ice, iodine crystals, solid methane, and naphthalene. If you look at the crystal lattice of dry ice, you'll see CO2 molecules arranged neatly but bound only by weak intermolecular forces. Now let's move to ionic solids, the category where we find salts like sodium chloride and potassium chloride. In ionic solids, cations and anions are tightly packed together and held by strong electrostatic forces of attraction. These solids are hard, brittle, and have high melting and boiling points because it takes a lot of energy to break these ionic bonds. In solid form, they don't conduct electricity, but the moment you melt them or dissolve them in water, free-moving ions make them excellent conductors. The stability of ionic solids is explained beautifully by the radius ratio rule, which tells us how the size of cations and anions affects their arrangement in the crystal. Covalent or network solids are the real giants of strength. Their atoms are connected throughout the crystal lattice by covalent bonds. Diamond is a classic example. Each carbon atom is bonded to four other carbons in a rigid three-dimensional network, which makes diamond one of the hardest natural substances with the highest melting point. On the other hand, graphite, another form of carbon, shows an interesting contrast. In graphite, carbon atoms are arranged in hexagonal sheets with weak van der Waals forces between the layers. These layers can slide over each other, making graphite soft and a good lubricant. Also, delocalized electrons move freely between the layers, which makes graphite a good conductor of electricity, unlike diamond. Let's turn our attention to metallic solids, which are the backbone of our modern world. In metallic solids, positive ions are immersed in a sea of delocalized electrons. This special type of bonding, called metallic bonding, explains why metals are shiny, malleable, ductile, and such good conductors of heat and electricity. The strength of metallic bonds can vary. That's why mercury is liquid at room temperature, while tungsten remains solid even at extremely high temperatures. If you look at the crystal structure of copper, for example, you'll see an arrangement that allows each copper atom to be surrounded by 12 nearest neighbors. This is what gives metals their typical density and stability. Now, let's compare them quickly. Molecular solids are soft and have low melting points. Ionic solids are hard, brittle, and conduct electricity only when molten or dissolved. Covalent solids are extremely hard and have very high melting points, except for graphite, which conducts electricity. Metallic solids show variable hardness, but they are universally good conductors due to their mobile electrons. These differences explain why common salt is used in food, why diamonds are used in jewelry and cutting tools, why graphite is used in pencils and lubricants, and why metals are used to build machines and wires. Let's quickly revise what we've learned today. Crystalline solids are classified into molecular, ionic, covalent, and metallic types. The type of bonding and the nature of constituent particles determine their key properties like hardness, melting point, solubility, and conductivity. These principles explain everyday materials around us, from the salt in your kitchen to the pencil you write with, the jewelry you admire, and the machines that power our lives. I hope this session helped you see the fascinating link between microscopic bonding and macroscopic properties. See you in the next class with more exciting chemistry concepts.